Hey everyone, and welcome. Today, we're diving into something your phone and computer do thousands of times a day, sorting. But this isn't going to be some dry computer science lecture. Oh no, we're going to pull back the curtain on the clever and sometimes kind of weird logic that makes it possible to organize millions of things in a flash.
I mean, just think about it for a second. When you sort a massive playlist or a giant spreadsheet, what's actually going on under the hood? It's not just a clumsy process of checking every single item against every other item. It's way more elegant than that. It's a series of brilliant strategies. And today, we're going to start with the absolute basics and build our way up, piece by piece, to something seriously powerful.
So to really get a grip on this whole sorting thing, you gotta start at square one. We're going to look at the most basic, most fundamental sorting problem you can possibly imagine.
Let's start with this list. It's just a bunch of ones and zeros. Now, if I asked you to sort this, how would you do it? I bet you wouldn't bother comparing every number to every other number, right? No, your brain does something way faster. You just count them. You'd see there are 7 zeros and 5 ones, and then you just write them out. All the zeros, then all the ones. Done. It's simple, intuitive, and incredibly fast.
And you know what? That simple idea you just had, it's a real algorithm, and it's called counting sort. It's basically a three-step process. First, you set up some empty slots to keep a tally. Step 2, you go through your messy input list and just count how many of each thing you have. And finally, you use those counts to build the final, perfectly sorted list.
Okay, so this visual here really breaks it down for us. We scan that input array, A, and fill up our counters array. So we find 2 ones, and bam, the counter for 1 goes up to 2. We see 3 fourths, so the counter for 4 becomes 3. And then that counters array becomes a perfect blueprint for our answer. It literally tells us, okay, write out 2 ones, 1 3, 3 fours, and 1 8. See, no complicated back and forth comparisons, just counting.
So, counting sort is awesome, right? Super fast, super simple. But it's got a pretty big catch. It's fantastic for simple numbers, but what happens when the stuff we're trying to sort gets, well, more complicated?
See, on the left, you've got your simple numbers. Counting sort eats that for breakfast. But look at the right. Now we have complex records, like student files. The problem is, you can't just count the age 20 and forget about Avraham's name. You need the whole record to come along for the ride. A simple counting that just says, I found 2 20s, just isn't going to cut it anymore.
Okay, so what do? We get clever. We upgrade our thinking. Instead of a simple little counter that just holds a number, what if we use something bigger, like a bucket, a container that's big enough to hold the entire record, name, age, the whole shebang?
And this visual, it's a perfect example of what we're talking about. This is bucket sort. On the left are jumbled list of students. In the middle are buckets, all lined up by score. So we take each student's file, like Avraham and Moshe, who both scored a 40, and we just drop them into the 40 bucket. And then for the final step, the big reveal, we just go through the buckets in order, from lowest to highest, and pour out the contents. Simple as that.
All right, now we're about to get into something that might seem like a small detail, but trust me, it is everything. It's a concept that acts like a secret ingredient, unlocking even more powerful ways to sort. It's called stability. So what on earth is a stable sort? It's actually a really simple promise. Basically, if you have items that are tied, like 2 people who are both 20 years old, a stable sort promises to keep them in their original order relative to each other. It doesn't shuffle them around for no reason. Let's make this crystal clear with an example. Now pay attention to the original list here. It's already kind of sorted alphabetically by name. See how for the 20-year-olds we have Avraham, then Dina, then Yitzhak? That's their original order. Remember that. Okay, now watch this. We run a stable sort on this list. But this time, we're sorting by age. The list is sorted by age, for sure, 18, 20, 30. But the magic is right here, with the 20-year-olds. Their original alphabetical order, Avram, Dina, Yitzhak, is perfectly preserved. An unstable sort might have given you Yitzhak, then Avram, then Dina, who knows? But stability. Stability respects that original order. And this one idea is the key that unlocks our final, most amazing algorithm.
Okay, so let's take stock. We've got counting, we've upgraded to buckets, and now we've got this crucial idea of stability. It's time to put all those pieces together and build something, well, something kind of mind-bending. So here's the final boss battle. How would you sort a massive list of really long numbers, like phone numbers or social security numbers? Is there some trick, some way to do it without ever actually comparing one whole number to another? Sounds impossible, right?
Well, believe it or not, the answer is yes, and the algorithm that does it is called radix sort. And its secret is that it works in a way that feels totally backwards. Instead of starting from the left, the most important digit, we start from the right, the least important digit. And we sort the whole list over and over again, one digit at a time, using our trusty stable sort.
Okay, here we go. Here's our messy, unsorted list of numbers. Let's see what radix sort can do.
Pass 1, we're going to look at only the last digit, the ones column. We totally ignore everything else. After a stable sort on just that column, look what happens. The list is now ordered by that last digit. See? First the 2s, then the 3s, the 4s, the 6s. It looks like chaos, but we've laid the foundation.
Okay, round 2. Now we sort by the next column, the tens digit. And this is where you see the magic of stability in action. Look at 4932 and 6492. They both have a 9 in the tens column. Because our sort is stable, it remembers that 4932 came before 6492 in the last step, so it keeps them in that order. It's preserving the work we just did.
All right, pass 3, moving on to the hundreds digit. It's the same deal, a stable sort on the third column from the right. You can literally see the order starting to bubble up to the surface. The list is getting more and more organized. It's getting closer, just one pass left. And here it is, the final pass. We sort by the thousands digit, the most important one. And boom, there it is, a perfectly, beautifully sorted list. And think about what we just did. We never once compared two full numbers against each other. We just sorted one column at a time, and the magic of stability took care of everything else. It's amazing.
So let's just quickly retrace our steps, right? We started with this super simple idea of just counting things. Then we upgraded to buckets so we could handle more complex stuff. Then we discovered stability, the secret sauce that makes sure existing order isn't messed up. And finally, we put it all together to build radix sort, this incredibly powerful algorithm that sorts digit by digit.
You know, this isn't just some abstract computer science puzzle. This logic, it's literally all around you. It's in your email when you sort by date and then by sender. It's in your social media feed. So the next time you sort anything on your phone or computer, maybe you'll have a little picture in your head of this amazing, invisible dance of buckets and digits happening just for you. Thanks for watching.